Great, thanks for the introduction, Michael. So as Michael said, I'm a new assistant professor in the mechanical engineering design group and teaching classes for the product design program and also around kind of the intersection between HCI and design and the physical world. So anyway, today I'm going to talk a little bit about some of the work that I was doing at the MIT Media Lab during my PhD and postdoc, and then also briefly talk about some directions of the things that are going on at my lab here, which we're tentatively calling the physical interaction group, but we'll see. Anyway, so before I get started talking about sort of what I've been working on, I think, looking back to sort of the rich history of tools and thinking about where tools come from is something that I think is really central to our role as designers of objects and of interfaces. And so these are hand axes that our ancestors made, many years ago. And these were made not only to fit, their hands, but also to fit the task at hand. And we've evolved with tools, and tools have evolved with us. And so over time, all of these tools have become increasingly specialized, and designers of these tools have gotten really good at matching their physical form to both how they want to manipulate the world as well as how you want to hold them. And so the physical form matches the functionality and can harness the richness and dexterity of our hand. But again, tools not only allow us to manipulate the world, tools can also be used to build other tools that can help us think about problems and think about space and think about interacting with other people. But as tools have become more complex, we've designed really great ways to allow for the manipulation of different parameters while you're attending to different tasks. And so these physical affordances that designers have gotten very good at creating really allow us to do many different things while we're not necessarily focusing on them. And the best interfaces are really those that sort of blend into the background or sort of become part of the task itself. However, I think the computer has really changed the way that we interact and also changed the way that we think about tools. Pretty much, most tools that we use on a daily basis now are either on a computer or use computers as part of the process. And the thing that's really changed about this is that computation is dynamic. And so as such, it can do millions of different things. So, your standard computer can have, there are millions of different applications that can run on it. But most computing systems really have the same static physical affordances for all of these different applications. So you're using the keyboard and the mouse or multi-touch interaction for both, composing an email as you would be for playing a musical instrument or playing a game or browsing a large data set or modeling something on a computer-aided design tool. And so I think that this is fundamentally a problem. And so my belief is that we need computers that can physically adapt to us to match their form to this dynamic computation as well. And that's what I've been working on at the MIT Media Lab and now hope to be doing the same thing at Stanford. And so at MIT, together with Daniel Leithinger and my former advisor Hiroshi Ishii, we built this system Inform that allows you to take digital information and make it now physical so you can interact with it directly. And you can use that to visualize 3D information that you can touch and feel in different ways. So for example, you can understand the slope and curves of a math equation as opposed to just seeing it. Or users can interact directly through touch and gesture to sculpt digital clay. And so you can use your hands in different ways that you wouldn't be able to with a traditional multi-touch or mouse and keyboard interface. But in addition, physical interface elements can appear and disappear on demand. And the idea is that for all these different applications, the physical form can reflect these things. Is there a way for me to have the video show up here? Sorry to interrupt. I think you can get it up there. Yeah, it's switching between me and the thing. It's hard to, because there's videos I need. For some reason, Keynote doesn't show you the video preview, so it's best if I can see it. So my apologies while I try to figure out this. But anyway, regardless of that, not so important. So anyway, as I was saying, we want the physical form to really match the way that we want to interact with it and to match the application. And so in-form can really change the way that we interact with information because now we're making information physical. And so how might we, use this type of system in a more practical application? So Tony Tane, who is a master's student at the Media Lab, worked with Daniel and I to create this system called Cityscape, which allows urban planners to have a physical model of their city. And now, as opposed to having this static physical model that they build, they can move around it. And then it can also become dynamic. So you can manipulate the buildings physically, but you can also look at different data sets and view those as they change over time. And so the idea is to really take sort of some of the things that we're already doing in the design process in urban planning, that is building these physical models and being able to collaborate with other people by spatially referencing them or manipulating them physically. But now we can add back in that digital component that allows you to have this rich computational abilities underneath. So obviously there's been a lot of work that this is building on and a lot of work in the space of sort of tangible interfaces that sort of started out of a collaboration with George Fitzmaurice and Hiroshi Ishii and Bill Buxton at University of Toronto, and then Hiroshi Ishii, my former advisor, had worked on a lot, and with many other people as well, but thinking about how you can represent information physically. But a lot of the limitations of these systems were that the computational system is dynamic, but these physical interface elements are not. And so there's been a lot of work before this as well in sort of haptic interfaces to give you that more interactive, yes?
What frame rate these sort of 3D interfaces run at?
Sure. So it's a little, the notion of frame rate is kind of interesting to think about in the physical world because you can update something very quickly, but then it might take time for that physical thing to actually get there. So the refresh rate on our shape display actually depends on the direction that it's moving in. So for example, if you're trying to raise something up, it takes longer than move down because of gravity. But we're able to refresh it around 30 frames per second. So that's kind of the refresh rate there. For other types of haptic systems where you're thinking more about actually manipulating it, you want to have even higher bandwidth and higher refresh rate because our tactile senses are actually much faster than our visual ones. So tangible interfaces. And a lot of these really stem from learnings about cognitive science and how we think about problems and how we can offload those into the physical world. And so one of those notions is this notion of epistemic action, so being able to externalize our thoughts into the physical world. And so there's been this rich history of tangibles. And then more recently, in addition to the haptic interfaces that have been going on for a long time, there's been work in sort of actuated tangible interfaces, which can use, in the case of Pico, which was from the Tangible Media Group, uses magnets to move around these physical objects. Or for example, Fabian Hammert's shape-changing mobile device uses servo motors to give you feedback on these things. However, most of these examples can sort of only change between a few different states or are limited to sort of 2D interaction. And so another direction that's been really exciting that we've built on a lot is this notion of shape displays, where as opposed to sort of a traditional haptic interface where you might have something like the haptic phantom, where you have a tethered device that's giving you force feedback. Here the idea is to create a tactile display that you can touch and feel with your hands, but you can also see it. And so that means that it can allow for multiple users to interact with it and other things like that. So Project Felix is one of the first ones of these, but there's been a number of others such as Ivan Pompirev's Lumen and then a lot of the work from the Media Lab. However, a lot of these systems have really focused on only thinking about how you display 3D information information. And so really the focus of our work has been to think not only about the content, but also how do you create new types of user interfaces and user interface paradigms for these new types of systems. And so one of these things sort of is this central concept to a lot of things that I've been working on is this notion of dynamic physical affordances, that we want to have physical affordances that can allow the user to both understand how they can use the system, but they need to adapt to these different applications. And so some examples of what these could be on the Inform shape display, which is sort of this kind of low resolution prototyping platform that we built, are you can render sort of buttons or sliders on demand, and then they can become they can change their position and resize, and they can be touch sensitive as well. Or they can morph between input dimensions. So you can have a button that can then become sort of this touch selector. And so it gives you this continuity between them. Or they can also be context aware. So you can have them resize based on how close you are, sort of this target expansion that's been done in mouse and keyboard interfaces, but now we can do these types of things in the physical world. And so these parameters of these dynamic affordances, we can really manipulate a number of different things. So we can change their shape, their size, their position and orientation, their color, their visibility, as well as the way that they feel, so their haptic feedback. So we can change the stiffness as you're touching it. And I think what's interesting about this is that shape displays really allow us to have a much when we're coming from thinking about graphical user interfaces, they really allow us to have a better way to map these traditional interfaces into now 3D interaction that can become physical and material. So, for example, the software stack that we built is very similar to how you would program a traditional graphical user interface. But we can also do things like appropriate existing objects as interface elements and use the shape display to move them. So for example, we can have a scroll bar or a play bar where the play bar is actually moving the sphere, and then you can interact with it as well. And so the idea is not only to use the shape display to display these dynamic affordances directly, but we can also use appropriate passive objects as well. And so that means that we can do things like move objects around the table. So for example, if someone receives a phone call, but they're not looking at it, then you could actually sort of move the phone move the phone to them. So this is kind of like a little fun example. And so all of this is built on this Inform platform that Daniel Leichtinger and I built. And so it's kind of this brute force approach to how you might build one of these systems. So it uses 900 linear actuators and then these mechanical linkages to get a higher resolution in a smaller or in a larger footprint at the bottom. But this isn't how we envision these being built in the long term. Really, we're interested in using these to prototype new types of interactions and applications. So this is sort of how we did it, but not necessarily how one would do it if they wanted to make a product or something. And so yeah, as I mentioned, there's 900 actuators, and we ended up using these ALPS motorized slide potentiometers for the actuators because they're inexpensive, but you can also backdrive them, and they're very robust. The other thing that I think is one interesting aspect of the Inform system versus prior shape displays is that it's quite fast. And I think that speed really allowed it to have this interactive quality that we were going for. So that was something that I think a lot of the other shape displays have kind of slower types of actuation, like shape memory alloy or pneumatic systems. But here we really wanted to have something that was fast. And so we went with these, yeah?
I'm just curious, was that designed in from the beginning, or was that sort of like you got there and then realized what you had on your hands?
In terms of the speed, or? So I think definitely we wanted it to be interactive, but we've spent a lot of time thinking about like why did this work so much better or was more compelling than other shape displays. That, for example, Lumen, which is Ivan Popyarov's system, I think is really great and really exciting. And it has actually a very similar resolution. It's smaller. It doesn't have as many pixels, but it has about the same resolution. But it is much slower. And so I think that we did get a little lucky that there was this nice sweet spot of sort of speed, cost, and the number of actuators that we used. But I think it's also interesting. So previously, Daniel had built a lower resolution shape display. And that really didn't allow us to display very many things. And so this kind of step to the next resolution, it wasn't an order of magnitude, but somewhere close to that, I think really got you a lot. And so I think similarly, you'd find that if you jumped down another step, you would probably find even more interesting applications that we can't really do with this just because of the scale of the pixels. But yeah, in terms of shape displays, I think there is this trade-off between sort of the number of actuators that you're using, the cost, and then the speed or force. And so it's kind of this interesting space to work in. So then we developed these custom motor drivers, and it's all connected over this RS-45 bus, and then we can update it at 60 frames per second, although, with the motor speed, as I mentioned before, it kind of changes things. And then we have a depth sensing camera from above to track input. And then we can also sense the position of the pins for interaction. So after building this system, one thing that we thought a really interesting application for this was collaborative design and collaboration across distances. And so because when we're interacting in person, we use physical objects, we sketch on paper, and we aren't just looking at someone's face. So we're trying to think about how we could have a richer sense of collaboration at a distance. And one of the advantages of these shape displays is that you can do something across a distance like that. So Daniel and I worked together on this notion of physical telepresence. So how could we create this shape display system that could both not only display content and user interface, but could also display a remote person as well. And so as I mentioned, when we're collaborating in person, especially around design tasks, we have physical artifacts and space that we really use as part of this process. And I think that there are in this space people, objects, and tools, and then the environment as well. And when we think about what we imagine remote collaboration to be like, maybe we think more about this sort of Skype-based windowing metaphor. And obviously, there's been a lot of work in telepresence and shared workspaces. Obviously, I see John Tong there, who's done some great pioneering work there. But we're still sort of limited to this screen-based interaction. And so the question is, how can we use these shape displays to now enable this type of rich collaboration that we have in person, but at a distance? And so we think that there's sort of 4 aspects to this approach that are really important. So one is physical embodiment. So how can we capture and remotely render a person's body parts and gestures using this system? So here you can see that we use the shape display to represent a remote user's hands. Second is interaction with synchronized remote objects. So here, if you have 2 people that are collaborating, you can actually manipulate the same linked object, and then that will get translated across distances. Then thirdly, we want to talk about how we can go beyond this one-to-one mapping of a representation of a person to expand their capabilities. And so this notion of beyond being there physically, how can you actually make the person who's remote have more capabilities and be better than if you were collaborating in person? So some of these things are around like changing the scale or giving people multiple arms. And then finally, how can we manipulate shared content by deforming it directly? And so here you can think about having 2 linked 3D models, and you can collaborate them as well. And so as I mentioned, there's been a lot of work in shared workspaces and physical telepresence that have really inspired us. So as I mentioned, video whiteboard, big inspiration. Also Hiroshi Ishii's work on Clearboard and many other systems allow you to have this richer sense of interaction, but still don't have the physical side of things. So then there's been a lot of other systems that have looked at how you can have embodied remote collaboration through, for example, robotic telepresence, but then also some work on tangible remote collaboration. But here, really the physical telepresence through telerobotics has focused on, mobility. So how can you have this physical embodiment that can move around a space? And the tangible remote collaboration has sort of focused on the shared workspace. And so what we wanted to do was sort of focus on this shared workspace, but have more of this physical embodiment of a remote user. And so to do that, we're using these shape display systems that I've previously described. So in terms of physical telepresence, we can, as I mentioned before, use this to represent content, and then we can spatially reference the content. We can actually manipulate objects at a distance, simple objects. Then we can have linked objects, and then we can augment people's capabilities, trying to go beyond being there, and then also manipulate shared content. So first I'll talk about this spatial referencing and annotation. And the idea is really to have this common ground that people can together reference and understand and think through problems by having this physical representation and being able to manipulate that, as well as being able to see spatially where you're interacting. So the way that we're able to do that is that we capture a remote participant using a depth sensing camera, and then we can represent them on the shape display as well as content. So here you can see we can have this low resolution model of an aircraft, and then I'm able to actually spatially reference it in 3D. And so that can really help people collaborate and discuss around 3D information. But we can also provide that remote user additional displays so that they can sort of see what's going on. So here we have a 2D display that's showing a top-down view of the remote system, but that allows you to really have this spatial referencing abilities. But I think what's really important about this system is that now, as opposed to you could imagine doing something similar to that if you had some type of 3D display or augmented reality. But really now with the shape display, we can actually manipulate objects that might not be virtual as well. And so, for example, you can reach out and lift up an object and manipulate it. So that allows you to spatially reference and then also manipulate these objects. And so there's different ways you can manipulate them with the system. And then here's sort of what the remote side sees. So a lot of the things we were doing, because we only had one shape display, was this one-way interaction. And so you can kind of have improvise with different objects as well. And then you can start to manipulate more complex objects. A lot of the limitations here in the manipulation have to do with the degrees of freedom of our display. So if you have a robotic system, then you have 6 degrees of freedom. Here we have 900 degrees of freedom, but they're all in the same direction. So we have a little bit of redundancy there, but it allows us to do things like, for example, improvise with physical objects. So for example, here you can take a bowl and then use that to manipulate something at a distance. So you don't have to just use your hands. I think that sort of starts to speak towards what here is interesting beyond telemanipulation with a robotic system is the flexibility of it to change the end effectors or to change the material that you're using with it, that it starts to become more like how we interact in person. And so, we're also interested in this bidirectional interaction and display. But as I mentioned, we kind of only had one shape display, so we split the display in half, and then, but the nice thing is that you can, take objects and then they can appear on both sides, and you can, go in and manipulate them. But we have sort of the same limitations in terms of the input side as well, that we have 900 or 450 if you divide it in half degrees of freedom of input, but it's all in one direction. And so we thought about different ways that we might be able to manipulate objects at a distance. So this is a brush tool that then allows you to push objects as opposed to just pressing on them. And so then we tracked the direction of the force, and then there's a switch on the brush that tells you if you're pressing on the object as well. But then, as I showed previously, we can think about linked objects as well and manipulating those. So here we can have these synchronized tokens, and we can also represent the user's physical presence as well. Or we can, just have the graphics, but then manipulate them. And so you can kind of have different ways of representing things. And, really, I think what we want to do is not only make collaboration as good as it is in person, I think we can really start to think about how we can make a richer type of collaboration. And there's this great paper, Beyond Being There, and I think we can start to think about that for this type of physical telepresence as well. And so we were really inspired by things like Stellark with having a third arm, or this scene from Ghost in a Shell, where you have like 1,000 fingers, or things like more practical things like the Da Vinci surgical robot, where it'll cancel out tremors and allow you to remotely do surgery. And so we wanted to think about how we could go beyond these bodily limits that we have. And so we can change the output modality of the person, so we can allow them to sort of move around objects by becoming kind of ghost mode is what we like to call it. But that allows you to sort of not knock over things. But then that can also be useful for like referencing on top of things due to our limitations that you can't actually move above something. But then we can also have different transformations, as I showed previously, so you can scale or rotate a person's hand, which could be useful for, or mirror as well. So this could be useful, for example, if you have a larger object, then maybe you need larger hands to manipulate it. And so you can go in and scale those hands up. That allows you to actually have more force then as well. And then on the remote side, you can actually, you zoom in and out of this scene, and then you can see the smaller version as well. So these mappings sort of work across these things. But you can also think about replicating hands. So here I can, if I'm helping someone with a soldering task or something, I can lock a hand and freeze a hand there, but still have two hands to do something else. But then we can go further and sort of replace people's hands with other types of representations. So kind of as I mentioned, as opposed to a robotic telepresence system where you might have one type of end effector, here we can have end effectors that we can manipulate on demand. So we can replace a user's hand by tracking it with these different types of end effectors. And obviously we're limited by the resolution of our display, but I think it's interesting to think about the flexibility that this has versus some other types of systems. And finally, we can also think about how we can have shared content that we're able to then manipulate as well. So if we had these are two lower resolution shape displays that we had, and so the idea is if you had two higher resolution ones, you could have a shared physical model that you could then manipulate across distances. And I think that's something that we're working on now at our group at Stanford, is thinking about how do we build these higher resolution shape displays that can allow for more collaborative design at a distance. And so, as I mentioned, these are all built on this Inform platform, but the basic system diagram is that we capture the remote person with the depth sensing camera, and then we have these feedback screens for them in the asymmetric teleoperation setup, and then we send that data over the network or on a computer to our shape display, and then we can project content on that there. And then the bidirectional system is very similar. And for that, we used this transform system, which we built for this Milan Salon, for the Milan Design Fair, which is basically a lower resolution shape display, but has multiple segments. So we used that for that. So we did some preliminary evaluation to see, how could people actually manipulate objects at a distance? Would that work? Because there's a number of limitations with our system, some of which are fairly obvious in that the pins can only move up and down, and normally when we push things, we have, forces kind of, in contact with the object as opposed to just sort of moving it, tilting it. Then also the refresh rate of our display is somewhat limited, and so for these systems you have for teleoperation, you want to minimize the latency. We have a fairly high high latency, and so we wanted to see how could people interact, and then what are the ways that they would use this system to manipulate objects. So here's the sort of test setup that we had, where we had on one side, the asynchronous control side, where you have this view, and then on the other side you have the shape display. And then we wanted to see if the lack of this haptic feedback, so you can't actually feel what you're manipulating either, and the latency would present problems, and to see what types of interactions people would use to manipulate objects. So we had 3 different conditions, but the details are in our paper. But basically, some of the interesting things were, the different ways that people were interacting with these things. And so you'd see these different, creating these different shapes to enclose things, or using the back of your hand. And what I think this speaks to is sort of the flexibility of the system, because you can have this freedom to manipulate these things in different ways. But obviously, I think there are a number of limitations with this type of approach versus something like a telerobotic manipulation system. And a lot of those stem from the shape display itself, like the resolution of it, the limited degrees of freedom, and that you can't really grasp objects as well, and the cost of such a system, because it has so many actuators. But I think it's really points towards a new way of thinking about this type of telepresence. So in the future, we think we could have 2 of these higher resolution ones, as I mentioned. And also we can connect it with augmented reality, so you can have richer 3D graphics on top. And so we had a Kai paper that was about some of that before. And then we also installed this setup at the Cooper Hewitt Design Museum. And so we recorded interactions with people manipulating things. And so we're looking through there also to kind of understand, for a walk-up scenario, what are the interesting things that people are doing. So I think, to me, shape displays are this kind of exciting area that allows you to do so many different things with it, to render 3D models, but also create these new types of interfaces. But they're all kind of have the same form factor of 2.5D resolution with an array of actuators. So right now, we've been thinking about what are different form factors that we could create to create new types of shape-changing displays that might be allow for new types of interaction. And so I'm quickly going to talk about a project that Ken Nakagaki led, that I was co-advising with Hiroshi while I was doing a postdoc at the Media Lab, that he's going to be presenting at WIST this year. And the idea is, as opposed to having a shape display where you have all of these degrees of freedom which are in this 2D array, here we have a 1D array of actuators that can then create a curve that you can manipulate. And so that can look like, whoops, I clicked twice. So that can look like this. So here you can have this system that you can manipulate, but it can also snap into different shapes. And it can also do so, not as, drastically. So we can use that for mobile interaction, for kind of physical feedback, or other types of interfaces. And so, we were really inspired by, snake robotics and looking at the kind of different types of geometries that people have used in continuum robotics and other types of robotics, and how can we then apply some of those to interaction. But there's also been a lot of work in art that's used these really beautiful kinetic installations of line to convey information. So not only to in the snake robot case to manipulate things and also move across distances, here we can use lines to actually display information. And then obviously there's been some work in HCI thinking about how might you interact with deformable curves, and then some work also on how you might use a curve to display information. But there hasn't been so much work on this as to date. And so we think there's really interesting possibilities for this in terms of display. We can use a line to create lots of different shapes, both in 2D or in 3D, or to create solid volumes as well. And those can be used for things like data visualization, to represent iconic forms, or also to create interface elements, as well as creating ergonomic forms, or things that provide aesthetic value as well. And then we can interact with these curve-based displays in a variety of ways. And so we can deform them, we can touch them, we can pinch them. And so there's a lot of different interactions that are possible when you're thinking about a curve versus a solid versus only touch on a surface. And then we can actually use them to constrain our interaction as well. So here's some of the prototypes. So we have two different versions. One is this larger version, which has 2 degrees of freedom per joint. And so that can create these 3D shapes. But then we also have a smaller version, which is only 2D, but then it's higher resolution. And so these are sort of the different characteristics between the two. And so we don't have input sensing on the smaller one, but it gives you this much higher resolution. And the way that this works is that we have this array of servo motors that are connected to each other, and then they talk to a computer. And so here's some of the applications that we've explored with them. So one is using it as a mobile device. So it can actually, be this wristband that can give you notifications, but then you can sort of unwrap it, and then it can sort of change into this touch-sensitive input device, for kind of more touch-based interaction. And then it could actually change into the sort of the shape of a phone. And so this is Ken who did most of this work. And so the second direction that we've looked at is, how can we create shape-changing chords that might be able to both be used as input and as output. So here you can have this adaptive chord where you can have parts of it become the interface itself. Or we can use these same types of chord-based interfaces to display information. So this is connecting to a laptop. So you can, as you drag a file, it can give you feedback there as well.
How about biological applications?
Yeah. So in terms of human scale, or?
No, I'm thinking of proteomics, macromolecule modeling.
Yeah. So definitely. So there's a lot of work in thinking about folding and thinking about, kind of using protein folding, not only to solve problems in biology, but also as a way of thinking about new mechanisms for, designing human scale devices and also things like that. So I definitely encourage you to look at the Center for Bits and Atoms at MIT that's been looking at a lot of things inspired by these molecule and protein-based systems. So they have this cool project called the millimoteins, which are these different reconfigurable chain systems. And so then the video that was shown here is thinking about how you can use that for interactive feedback and control, but you can also constrain interaction on a 2D surface as well. So here's this kind of smart ruler, so you can create these lines of different sizes and shapes and things like that. But I think it's interesting to think about how we can also augment traditional practices as well. So because it's in the physical world, we have this flexibility. And then finally, we can use this type of thing for computer-aided design as well. So here you can have, as you're manipulating this curve in the physical world, it can be transferred to the digital world, and then you can do things like, snap to grid, physical snap to grid, or rendering hinges, or mirroring. And so all these things that you can do that we've developed these wonderful interaction techniques for in the digital world, we can now take those to the physical world, which is interesting. So finally, I want to just really quickly run through some other work that we've been doing kind of in the mobile space. And some of that's been going on here at Stanford. But I think really, as we've seen this trend in computing moving from, the desktop to our mobile devices, more and more we interact on the go. And I think that still the mobile device, an iPhone, there's over 1 million apps in the App Store, but it has this same static physical interface. How can we adapt some of these techniques to these different, to the mobile application? Yes?
I was just wondering about the snake thing that you showed. What kind of resolution can you expect from that? I mean, you showed us a couple of examples where they were like using it for 3D modeling and stuff, but what kind of resolution does it have?
Yeah, certainly. So I think that, again, a lot of the work that we're doing so far is really not thinking about, what are the techniques or technologies for implementing it today, but rather what can we do with the technology that we have today to explore these new types of interactions. And so the current prototypes, the shape display as well as the line form, are very low resolution. But I think, along the lines of what I was talking about in terms of stuff that's going on at the Center for Bits and Atoms and also in soft robotics and these types of domains, I think there is a lot of exciting work going on in robotics in thinking about different scales, and we can benefit from this as well. But so to answer your question of the exact resolution of our current prototype, I think it's about 2 centimeters is about the resolution of the small one. So as I said, we want to have this more rich mobile interaction. And so this was a project with Lining Yao that's called NUI, which uses pneumatic actuation, kind of similar to the application that was shown in the line form, where it can change shape between this wristband to this. But here it uses less actuators, but with smarter materials that can give you this richer shape change. And then also, we can think about devices where we can actually reform them ourselves. So as opposed to having a system reform them, we can use different techniques to allow users to change the shape. So this is a project from a WISP paper from 2012 about jamming user interfaces. So we could detect this shape that we're deforming something into and then lock it into these shapes using this jamming technique, which changes the stiffness of materials. And then finally, we're working now at Stanford on thinking about how we can take some of the ideas from shape displays and use them as tactile interfaces for mobile devices. So this is a project led by Sungjun Jang and Lawrence Kim and Kessler Tanner that allows you to have both in-pocket tactile interaction as well as in your hand. So we can just the same render these dynamic physical affordances, and you can interact with them, and you can create these buttons that you can touch and interact with. And then inside, we have all these linear actuators to give you this tactile feedback. And so finally, I think it's clear to me at least that computers are really everywhere now. They're on our desktop, they're in our pockets, but increasingly they're in our walls in pretty much every device we buy. And so I think it's interesting to think about, as opposed to just interacting with computing, how do we interact with our environment, and how do we have our environment physically adapt to us as well? And so Daniel Hiroshi and I built this system called Transform for the Milan Furniture Fair, and then Luc Vink and Ken Nakagaki and Virj Khan made this interactive prototype to think about, how can we have furniture scale interaction where we have this type of adaptive physical system, where as you bring a device over to it, it can adapt to you and provide the physical affordances that you need. But you can also use it to display information and move objects around as well. And so the idea is to think less about this notion of the future of computing, and instead think about the future of our environments. And so this is sort of a music display application, and I think the next one is my favorite. So Ken built this. So it actually really does work, that it'll flip these cards over, which I thought was kind of amazing. So I think this sort of, to me, points to a new way of interacting with our environment, where we're not only sensing people in space, but now we can actually physically interact and physically output things in different spaces. And to me, where this points to is this notion of maybe thinking about how do we move from the current age of ubiquitous computing to thinking about ubiquitous robotics. And so just as computers don't really look like this today, robots probably won't look like this in the future. And so how do we as designers and human-computer interaction experts start to think about this coming trend of increasing amounts of robotic devices in our lives, and how do we think about those not just being used for mobility, but now for interaction and really trying to enrich our lives? And so I think this is across scales from thinking about the interaction on your body, robotic interaction on devices, all the way up to environments and furniture. And so, as I said, it's sort of this space of human-centered design, robotics, and sensing, as well as interaction techniques that I think points this way forward that could be very exciting around this notion of ubiquitous robotics. So in conclusion, I believe that we really need computers that can physically adapt to us. I, for one, am fed up with the ways that we interact with computers, and I think that there's a lot of possibilities to really learn from and build on the cognitive science of how we understand information and how we can manipulate things in the physical world. And I think that's a really exciting direction for me. So with that, I'd like to thank my many, many collaborators on this, and I'd be happy to take any questions.
So in terms of deforming the informed display, right, you can like push down on the pixels, and I assume the opposite direction would be like to try to pull up on it.
Yeah,
now, of course, pulling has, of course, a lot of limitations compared to pushing, because you can only pull one thing at a time, and it needs to be like in a place where it can be grippable.
Yeah,
right?
definitely.
Have you considered like addressing that limitation?
Yes. So I think that is a big limitation in the way that you interact with these systems. So we have actually thought a lot about that. And so Daniel has a paper from WIS 2011 that's called, I forget the exact name of it, but if you look up Leitinger 2011, that talks about different ways that you can manipulate these shape displays based on this problem that, if you have concavities that are too small, or you can't pull up the pins. So some of the things that we've looked at are doing things with gesture, so you can use gesture to interact, but then also you can do things to sense where the user is, and then provide these dynamic affordances that allow you to manipulate things as well. So I think that that's a good point, and I think that it really does speak to, that's only one of the limitations of how you would interact with it. You also can't, apply force laterally or other things. So I think that there are still, a lot of limitations with these shape displays, and just now we're starting to think about how we might build interaction techniques to support more interaction. And some of those I think are, trying to solve the limitations of specific systems, but I think some of those are sort of key to this class of interfaces as well. So.
This is all really cool. I'm wondering, when it gets to consumer type products, based on this, what are your concerns and what we'll be doing for safety purposes? Because you had all these objects on this desk, and I'm like, this seems like a great way to send a cell phone flying.
Yeah,
or that, like, this,
so,
this snake.
I really want that. I want
Yeah. So I think that is a really interesting point, and I think beyond just the actual safety, so you could make this system safe, and you could make it, and I think also, in robotics, there's a lot of talk about this shift towards soft, compliant robots that are much safer than, other things. So I think there's a technological solution, but then there's also this, I think, which you identified correctly, is this psychological one as well, that, normally, other than other animals or, people, things don't really move or change shape very quickly in the real world. And so we've been doing a lot and running some studies to better understand, how do people perceive this shape change, and how can we sort of build in either feed forward into the system so we can clue the users into how things might be changing shape or how things might be moving, as well as what are the right speeds at which to move things. So I think there is a lot of interesting things to think about around that, and definitely an intersection with a lot of the stuff going on in terms of human-robot interaction, in terms of thinking about the safety and how the perceived safety of these systems. And so a lot of the work there is thinking about if you're collaborating with this robotic system which has arms or something, how do you when we're talking to someone else or interacting with a person, we actually there's a lot of lead in and gesturing and social cues that we pick up on that are how we don't surprise each other all the time. And so we have to think about how we can build that into our systems as well. So I think the social and psychological aspect, I think, is really exciting or interesting for us as a research community to think about. So, yeah.
I really like the tactic feedback and everything. I mean, if you think about like why nowadays, like there's a lot of touchscreens that everyone's using, but like there's a reason people are still using a physical keyboard because they know where their fingers are and everything. So I see that as like something that could be really, really successful. Like having a touchscreen that actually morphs, whatever. So like I just like if you could talk a little more about like timeline maybe of like something like that.
Sure. So, well, in terms of the keyboard that can physically adapt, there's a startup company, or I don't know if they're a startup or if they're just a company, but called Tactus, which is working on creating, basically a display, and it has basically these microfluidic chambers that inflate, and the index of refraction of the fluid is the same as like the glass, I guess, and so basically it can inflate these little bubbles over keys and stuff. So I think that's like a near-term solution, and I think they have. I don't know if it's actually in any consumer device now, but they've been around for a long time and trying to get people to put this in. But then I think it's possible with the shape displays that they could take a similar trajectory to something like 3D printing or computing in general, in that maybe there's these applications where they make sense for design or for geospatial information or something like that, where you have them in a workplace and it's a shared type of thing, but over time more and more people, the cost goes down and more people can have them. So that's one possibility. But I think that I think there's different ways to approach the commercialization problem. But I think it is a big challenge. Is a lot of this, basically display engineering has gotten so good that displays are so cheap, right? And right now, motors aren't that cheap. And so the question is there, this physical limitation to the price, or is it just that we haven't spent as much time engineering clever systems and also reducing the cost of these things? So,
well, this is a related question. What do you view as being the killer apps? And you can start with the sheet system and some of the other cool systems that you showed, and what kind of improvements to hardware and cost, economics would you like to see to enable those?
Sure.
The low-hanging fruit.
Yeah. So I think to me, really the low-hanging fruit or the applications where it makes the most sense is sort of 3D spatial information. So things like computer-aided design, things like geospatial information, things like command and control, where you have a lot of data that is 3D that you want to collaborate on, that you want to manipulate. And I think that computer-aided design tools have reached in some cases this sort of plateau where they haven't really become that much easier to use in a long time. And so I think this could really play a big role there. But then, how do we get it there even to that? So I think really you're going to need more resolution. And so I think one way to think about that is to move beyond sort of having M times N type of thing where you need so many actuators to trying to find a way to have something like a M plus N type of system. So if you have valves or something like that. So there's some work out of Georgia Tech on doing this type of approach where you can kind of go through the display serially to control it. So that's one thing, is just trying to find other ways to reduce the number of actuators. And so I briefly showed this NUI paper, which was about using pneumatic composites. And there's a lot of work in soft robotics also that are looking at how you can use fewer number of actuators with mechanical constraints to give you much richer types of motion. And so I think that's another possibility as well, is thinking about smarter ways as opposed to this brute force approach of having all of these pixels, which I think from a computer science and graphics perspective, we like pixels, we know how to interact with them, but there might be, that's not really how nature works, right? There aren't, these grid-based systems that you find in nature very often. So, John?
So I was really intrigued about the way you use that line robot to give sort of feedback wrapped around an arm. I wondered about combining that with like augmented reality or kind of a visual picture of something with that feedback.
Yeah. So I think that's a really interesting direction. We haven't tried it out yet as well. I think, there are some, in some cases, you could just think about it like an exoskeleton and a robotic exoskeleton. So I don't think, like, in terms of like the research, in terms of how you would do something like that, I don't think there's that much novelty there, but rather what I think is interesting about this is sort of the flexibility that you could, use it for different things. Like if you have a robotic exoskeleton, it's just a robotic exoskeleton. Versus this could be used for, interaction with curves or other types of things. But I do think, virtual reality is obviously really a big deal in Silicon Valley right now, and I think maybe this is the time that it takes off. We'll see. But I think a big part of that is once people are seeing things in 3D, they're gonna want to touch them. They want to feel them. And so I think that's definitely a direction that we're thinking about as well. Is how do you build cheaper types of haptic feedback for virtual reality?
You guys explored ferrous fluids to get the feedback?
Yeah. So we haven't personally looked at that too much, but there are some other groups that have for tactile feedback. So there's, I believe, Jan Borker's group had a project called MudPad, which trying to remember the name of the grad student. But anyway, so Jan Borkers and MudPad used MR fluid inside of a sealed flexible membrane, and then they had a number of magnetic basically electromagnets, an array of electromagnets that you could then feel differences in stiffness. So I think that's an interesting approach. I think, and you see these sculptures, I forget the name of the artists who do these wonderful things where you have like these really strong electromagnets and then they create these really amazing patterns around it. The thing is that the ferrofluid is actually kind of toxic, so you can't directly touch it. So you need to somehow wrap it in something. But I mean, that's very interesting. And so I think, I showed just, a subset of the ways that you could potentially think about these shape-changing interfaces. But there's, so many different types of actuation technologies that people in robotics are exploring and other domains such as art. And so I think it's really a exciting place to be thinking about. Michael?
We have coincident I/O on shape-changing displays. So, like, right, you think about these patterns with bendable displays or very, very small displays. Like, imagine the pixels are actually on the units. Is that far off, near? Do you think that's going to change, or is it going to be similar to what you see?
So I don't think it will change too much. So we're using projection mapping. And so I think, we're using a single projector. You could use multiple projectors such that you could probably solve a lot of the occlusion problems. So I think that there's a lot of cost in adding physical displays to this right now. And at the resolution, so where I think this sort of connects is, if you have something at the scale of Inform, it doesn't make sense to really add a single pixel per pin because it's so low resolution. So you'd want to add something like a screen. And there have been some papers, like Jason Alexander had this tilt display paper from Mobile HCI that was basically doing something like that, where you have like small LCD screens and then you move them. But I think really you want to have not only on the top, you want it all on the side. And so I think that, we're a little far away from having that kind of flexible display where it could be, very cheap. But I think, combining flexible displays with pneumatic actuation or with other types of actuation is really exciting. Unfortunately, the flexible displays are not really there yet in terms of they're flexible in that you sort of, at least the ones from like Samsung or that are commercially available, are like you can flex them like once and then they glue it in place. And that's what they mean by flexible. So I think there are, a lot of exciting things at this intersection, but right now the display technology is not quite there. I think 5 years from now it'll be a different story. So
it clearly takes a lot of mechanical engineering and other building effort to get these displays working. I'm curious, your own design process, like how did you prototype early on a display? Did you ever play with one of those Braille displays and see if you could do anything interesting with that first?
So the way that we approached the prototyping process was actually that we built a stop motion prototype before we even began building it. So basically, I think like the first month that I arrived at MIT, I was like, oh, I saw Daniel's lower resolution shape display, and I was like, oh, this would be awesome if we could use this for CAD if it was higher resolution. And so Daniel and I built laser cut, like basically made a giant pin screen toy and then made a stop motion animation of what could be the interactions for this type of thing. And then we had this video and we were like, oh, this is actually pretty compelling. And so then we also had this physical prototype that we could use for interacting with other things. So when we were doing the dynamic affordances, we would also like put stuff underneath and for creating constraints that you would move things in. So we did a lot of things with having this passive prototype before we actually built the thing. And then we did a lot of prototyping around different resolutions as well. So we would 3D print things at different resolutions. So more of it was on the kind of physical prototyping. And then for a later project for the Milan Furniture Fair, Philip Schussler, who was working on it with us, built basically a version of that system before we built it physically in, I think it was, trying to remember, I think 3D Studio Max. And so then he built a plugin that would allow you to animate things on 3D Studio Max, and it would get rendered on the shape display. And so you could prototype that before we even had the actual thing that we were building. So I think there's sort of two approaches. One is, how can you do this in software, and then how can you do, understand the physical thing? But yeah, we had played with some Braille displays, and we also had, Daniel had built this lower resolution one first. So I can't speak to what he did before that to better understand that, but we had that as well. So, John?
One final.
Oh yeah.
Bill, maybe?
More.
Yeah.
I'm picturing a Rubik's Cube with a display on every face. So you could solve it just by pushing a button and it would be the same color on every face, but then you wouldn't have to mess it up. It would mess itself up. Then you'd have to solve the problem.
Yeah.
A simple display, one color on each face. But it could also be instrumented. You could sense what you're. It's very satisfying.
Yeah, I love the feeling. The great thing about the Rubik's Cube and so many of these.
One hand.
Yeah, I can't do it with
Three
one hand.
cubes juggling.
Yeah, exactly. But I think, really the nice thing about the Rubik's Cube is you have this, there's this friction and I think maybe also detents, I don't remember. But yeah. So I think that would be really a fun type of interface. And yeah, Olivier Bao, who was working with Ivan Popirev for a while, he created this, I think they call it D20, but it was basically like a giant die. I think it's a D, I don't play enough role-playing games, so I don't know how they delineate the different types of things, but basically it was like trying to have input around this multifaceted object. And then Paul Pla, who is a Patty Mays' student, was working on these display blocks where they had displays on every side of the surface. But I think this combination of display and then manipulation is really nice. So yeah, thanks Bill.
All right. Thanks, Sean, one more time.